At this time, let me introduce Jeff Bennett, presenting Optical Fiber Capacity Limits. Where do we go next? Jeff is Director, Solutions and Technology at Infernera. This is Jeff's first time presenting at NADONG, and it's a pleasure to have him speaking with us today. Welcome, Jeff.
Thanks, James. Afternoon, everyone. I'd just like to thank the program committee, actually, for giving me the opportunity to present this tutorial, and I hope I'll do it justice. So let's get right down to it. I'll be starting with some basic terminology, but I did want to say that this is not really an optical transmission tutorial. It's about fiber limits. There is an excellent tutorial by Richard Steenbergen. Some of you may have seen it at NANOG 77. And it's online, it's recorded, of course. In fact, Richard's done a couple of these tutorials. So let me just remind everybody, I mean, you know, you guys are router people. I used to be a router person. I worked for Proteon and Wellfleet back in the late 80s, early 90s, and then 4 Systems. So I then transferred over into optical. And I used to draw networks like this, where we're connecting Paris, which is obviously in Ontario, and Berlin in Connecticut. There used to be a Berlin in Ontario as well, actually, until about 1917, I think. But actually, instead of that line, we really need to think that it's an optical network. It may be a simple point-to-point link, but there will be these elements of optical fiber connecting these 2 locations. And at the endpoints, there's going to be some equipment in the data center or POP. We're going to have something like a ROADM or a terminal. ROADM is an optical switch. And transponders, which actually put the 1s and 0s onto the fiber itself. Along the route, we have amplifier sites. In long-haul networks, typically these are every 50 to 100 kilometers. And this is a really important aspect of fiber capacity, as we'll see. The amplifiers themselves, one of the enabling technologies for DWDM, which is where we put lots of colors of light down the same fiber, was the Erbium doped fiber amplifier. And the key aspect was that this single amplifier is able to boost the power of lots of different wavelengths in a single device. If we'd have to have individual devices for every different wavelength, WDM would not be an economic technology. I also want to tell you the difference between client and line-side optics, because you may be a lot more familiar with client optics. So if we zoom into the transponder itself, which is the demarcation point between these 2, on one side you have client optics. And these are typically short-distance, single-channel, and Ethernet framed, 100 gig E, 400 gig E. You connect those into your switches or routers. On the line side, we have optics that are designed for much longer distance. They will be also designed to output multiple channels. Now, eventually this will be DWDM, but even on a single wavelength, you may be carrying multiple Ethernet services, because you could have an 800 gigabit wavelength, and it could be carrying 2 400 gig E services, or 1 400 gig E service and 4 100 gig E services. And so it will be framed appropriately. And that will attach into some kind of aspect of the line system, like a ROADM, an optical switch, or a terminal. And there will be lots of other transponders that join it, and that's how we get multiple colors onto the fiber. So client optics are very unlikely to reach fiber capacity limits, because they really just carry a single service. Whereas line-side optics, these are the devices that are much more likely to reach those limits. So why do you care that fiber has a capacity limit? Well, of course, when you look at these optical networks with lots of links in them, we know that demand is growing at a phenomenal rate, about 30% year on year. And some of these fiber routes are becoming full. You'll notice I put that in inverted commas, because different fiber pair operators will have different views about what full actually means. So I talked about amplifiers, and long-haul networks have to include these optical amplifiers. Typically, we use erbium-doped fiber amplifiers, or EDFAs. We also use Raman amplifiers, and these typically amplify in 2 bands, the C band, or the C-band and L-band. And most networks today are still using C-band, although it's becoming increasingly popular now to light up the L-band as well. And the bandwidth of the amplifiers will determine how much fiber spectrum we can actually use. So, I'll be explaining more about that in a moment. So historically, we were able to scale total fiber capacity by increasing the wavelength data rate or putting more and more wavelengths onto the fiber, or both, depending where we were in technical evolution. Because the fiber capacity is the product of the wavelength data rate and the number of wavelengths. And we may be approaching capacity limits in optical fiber today, depending on which routes we're talking about and how busy your networks are. So what are the limits and what are the options? I'm about to show an equation, and there's this old adage that every time you show an equation, you lose about half your audience, but stick with it because it's a pretty easy equation, really. It's the Shannon equation. I've simplified it down to two basic terms. And what we're really calculating here is the fiber capacity. Claude Shannon was a researcher at Bell Labs in the late 1940s. So obviously he wasn't working with optical fiber. He was working with wireless and telegraphy, copper cable technology. Optical fiber is a little bit different, but basically it will follow a similar trajectory. Because on the right-hand side of that equation, we have the bandwidth term, and that's how much of the fiber spectrum are we able to use, how much can we amplify. And then we have this term, the signal-to-noise ratio term. And the signal is how strong is the signal by the time it reaches the receiver. The noise, how much noise has been added during its journey. So it's a relatively basic and simple equation. There's a little bit of a glitch, because optical fiber is a non-linear medium. And that's different from the media that Shannon was researching. Air is linear, copper is linear, but fiber is non-linear. Well, what does that mean? What is a non-linear effect? So imagine you're listening to music at home and you keep on turning up the volume. At some point, that music starts to distort. It could be because your headphones are distorting, maybe the amplifier's distorting, speakers, whatever, but something is not able to handle that power level. And that's really what's happening in optical fiber. Above a certain optical power level, the signal starts to distort. It adds noise, which reduces the optical performance. And there are several different nonlinear effects. I'm not going to go into them because they are all bad, right? We want to avoid them if we possibly can. Now, the Shannon limit that some people talk about, when we're applying this term to optical fiber, I would suggest to you that it's not really a limit and Shannon was not involved because he wasn't working with a nonlinear medium. So what am I talking about here? Well, this graph on the vertical axis is showing capacity, and the horizontal axis shows optical reach. Optical reach is really important for network economics. What it means is the distance that you can transmit at a particular data rate without needing to digitally regenerate the signal. You can amplify. Amplifiers are analog. If you have to digitally regenerate, that's going to cost you a lot of money. So the curve will look something like this. The further you go, the lower the capacity of the fiber will be. And we can think of this blue line as the Shannon limit, which would be the capacity at a given optical reach if optical fiber was a linear medium, but it's not. So this is more like the limit that we're talking about. This is the capacity limit at a given optical reach when we reach the nonlinear threshold. So we've turned the power up, and just before it starts to distort, that's our limit. Now there's another limit which lies between the two, and this is the practical limit, this is the performance limit of a modern transponder. Because modern transponders have ways to either mitigate or deal with nonlinear effects. It's not perfect, which is why the green line is below the blue line. But we actually can operate, oops, hang on, let me just go back. We can, oh, that must be an earlier version of the slide. We can operate slightly above or slightly below that green line. There are definitely occasions, especially in submarine cables, where you might operate slightly above the line and you would implement nonlinear compensation, or you operate below the line deliberately. So how do we expand this capacity? We can look at the B term, or we can look at the SNR term. So if we plot out the bandwidth term, we see that it's nice and linear. So that looks like the best way to invest. Increasing bandwidth increases the capacity by a linear amount. If we improve the signal-to-noise ratio term, we are trapped inside a logarithm. And so we start to get a diminishing return as we improve the signal-to-noise ratio. And this is really where we're at in terms of things like transponder development today. We're starting to approach that limit. So what have we learned so far? Optical fiber is the only medium that we know that allows ultra-high capacity over long distances. We use multiple wavelengths to boost capacity. Optical fiber is a nonlinear medium, and signals will distort if we exceed certain power levels. And every optical fiber in the world has its own theoretical nonlinear capacity limit. We can better understand where to look for the best return using the Shannon equation. So now, we need to understand also that increasing fiber capacity will have an operational and financial impact. So what do I mean by that? There's really three steps in this process. The first step, which is the most desirable, is to keep the existing fiber and the existing line systems, the ROADMs and the amplifiers. Now, really, the only option you have there is to change the transponders and track the transponder evolution cycle. Option 2, keep your existing fiber, but consider bandwidth upgrades to the line system that will allow us to amplify more of the optical fiber spectrum. And then option 3, consider new fiber and new line systems, which is obviously the most drastic and expensive of these. So the technology evolution of the fiber that you have in the ground today is quite interesting because it's an asset that keeps on giving. So how does optical fiber work? Well, if we look down the end of a fiber, we might be able to see that there's actually an inner core and an outer cladding in the fiber. The cladding is made from pure silica, and the core has a little bit of germanium oxide in it, and that raises the refractive index of the core. So if you plot the refractive index profile, it's actually a gradient these days profile, and that gradient, sometimes people say that optical fiber works by total internal reflection. It doesn't, because the light wouldn't go very far if it did work that way, but the light is guided within the core of the fiber. That's why we say that optical fiber is a waveguide. Now, we make the core of the fiber very narrow, so there is only room for one path or one mode of propagation, and that's why we have single mode fiber today. By using single mode fiber, we avoid one of the most serious distortions you can get in optical fiber, which is modal dispersion. Some of you may deal with multi-mode fiber, and you know that signals don't go very far on multi-mode fiber. It used to be a lot cheaper than single mode fiber. These days, the difference is almost zero. Now, optical fiber, apart from being a waveguide, it really doesn't absorb much of the energy of the signal. We call that attenuation. How much of the energy of the signal is absorbed per kilometer of fiber? Well, let me give you a little bit of a thought example here. Assume there are 3.28 times 10 to the power 80 particles in the observable universe. Here's the question. If you have an amazing detector designer and they manage to design a single photon detector, and you have optical fiber like we had back at the beginning of the 1970s. The breakthrough in optical fiber was considered that if you could design optical fiber with loss of less than 20 dB per kilometer, you might be able to use it for communications. That was the kind of fiber we had back in the 1970s. So, how many photons, or how far could you go along fiber like that before you'd have to put more photons than there are particles in the observable universe in order to get one photon out at the other end? Well, those of you who like Hitchhiker's Guide to the Galaxy are going to be delighted here because the answer is 42, right? Now, 42 kilometers is not very far, and we have to put an awful lot of photons in there. And by the way, we can't build a single photon detector. So let's get more realistic. What about the fiber we have today? The kind of optical fiber that's designed today, like Corning's SMF28 ULL, this has a loss of 0.17 dB per kilometer. Much, much lower. Remember, the dB scale is a logarithmic scale, so this is a lot lower loss. So over a distance of 42 kilometers, to get one photon out of the end of that fiber, we only need to put 5 photons in at the beginning. So that's a big improvement on, 3.28 times 10 to the power 80. So a typical amplifier spacing is 100 kilometers, and we'd only need 50 photons into the fiber to get one photon out the other end. Well, actually, what about the number of photons that is normally found in a modulation symbol that comes out of a transponder? Well, actually, it's about 10 to the power 18 photons that come out of a transponder when you send a modulation symbol. So, this is really good news that optical fiber has this very, very low loss. Now, unfortunately, it doesn't have low attenuation across the whole spectrum. If we plot out the attenuation of the fiber, it looks something like this. So the lower the attenuation, the further apart our amplifier sites can be, and the better our network economics. Shorter wavelengths than that minimum there you see, shorter wavelengths are scattered. That's why the loss is much higher. Longer wavelengths are actually absorbed by the silica. So we have this really interesting situation where there are some anomalies. These are typically water anomalies. You can remove water from the manufacturing process of optical fiber, but it's kind of expensive to do that. You can buy low water loss fiber, but we don't use those wavelengths anyway, so typically you don't remove the water from fiber. There is a clear sweet spot here from about 1.53 to 1.65 microns, or 1530 nanometers to 1650 nanometers, which are the C and the L bands. So the C and the L bands, these are the sweet spot for optical transmission because optical fiber attenuation is so low. And we're getting very close with silica core fiber, we're getting very close to the theoretical minimum attenuation today. So in long distance transmission, we can only use as much of the spectrum as we can practically amplify. Now, some of you may be using shorter reach devices that use coarse wavelength division multiplexing, and you use much more of the spectrum, but you don't use it for higher capacity. You use it because it's cheap. But the things that typically are limiting us at the moment are amplifiers, particularly EDFAs. So an EDFA works in a very simple way. You have about 10 to 30 meters of doped fiber. So this is fiber that's had a little bit of a rare earth element, erbium, added to it. And so you've got your regular fiber that then feeds into this coil of doped fiber, and you use a very powerful laser to pump that fiber and energize it so that it amplifies weak signals and sends them out as very strong signals. And it sends out the whole band. It amplifies across a fairly wide band of wavelengths. And here we see the C band and the L band shown, and we need an EDFA in the C band, and we use a different EDFA in the L band. You can't quite get enough bandwidth to cover both bands at the same time, but C band EDFAs have increased their bandwidth over time. The very first EDFAs back in the early 90s had a bandwidth of about 3.6 terahertz. We then had 4 terahertz. Then today we're using 4.8 terahertz. And there are plans to extend that even further to 6 terahertz. It's known as super C band. It's in a single EDFA, so you're able to amplify 6 terahertz of bandwidth all at once. And then a similar thing happens in the L band. Typically, we just talk about L band doubling capacity. In fact, L-band is a bit wider than the C-band, but usually we do just talk about doubling the capacity. So Super C and Super L in a few years' time would give us about 12 terahertz of amplified bandwidth. And there are other optical amplification options like Raman amplification. And this offers very low noise, high gain amplification. It's more expensive. Some operators don't like to use it because there are operational procedures that you need to train your staff in for Raman. The Raman pumps are very, very powerful, and they operate in the infrared. So it can be shining into your eye. You don't know it because it's not visible, and it can be burning, damaging your eyesight. So there are lots of interesting operational factors with Raman. But it can be used for wideband amplification beyond the C and the L bands. And it can be used in combination with EDFAs. That's very common. It is commonly used today in long-haul networks as a hybrid Raman EDFA amplifier. There's a technology called SOAs, semiconductor optical amplifiers. They're very, very small. They're similar to a laser in size. They have excellent gain, but they have a higher noise factor than EDFAs. We tend to think of them as being very challenging for multi-wavelength operation. So like an EDFA will boost all of the wavelengths in the C-band at the same time. It's tricky to do that with SOAs, although there's been some work on SOAs where they think they can average out the noise, but generally speaking, they're not used as external amplifiers. They may be used as part of the laser chipset in a photonic integration design. So SOAs, interesting. They're definitely used within the transponder. They're not used in external amplifiers today. So what about using more of the grid, the wavelength grid, in a more effective way? So I'm going to be talking about fixed grid versus flexible grid. And we think really about DWDM in terms of like lanes on a highway. And how do individual wavelengths, how do the individual cars on the highway play nicely when there are other cars close by? How do the wavelengths share the spectrum? Well, from about 1995 to 2013, the only commercial approach was a fixed wavelength grid, or actually a fixed frequency grid. And total fiber capacity tended to be limited by the grid itself. So what happens over time is that the grid granularity got better and better as more granular wavelength multiplexing and demultiplexing technology became available. So we started off with grid spacing of 200 gigahertz, then that went to 100 gigahertz. A lot of you will be familiar with 50 gigahertz grid systems. They were very, very common for a long time, and there are some 25 gigahertz grid systems out there as well. The number of channels you typically get in a classic 4 terahertz C-band with those grid settings, 20 channels increasing to 40 channels, increasing to 80, increasing to 160. The more channels you have, the more fiber capacity that you have. So what happened at some point is that we moved away from fixed grid because there's some key information here. You can increase the data rate of a transponder by sending modulation symbols more quickly. We call that the baud rate, the rate at which you send modulation symbols. If you have a higher baud rate signal, it is wider. It occupies more frequency. In fact, if you double the baud rate, you double the spectral width of the signal. So if you now apply this to fixed grid WDM systems, this is 80 channels at 50 gigahertz. So this is a very, very common grid pattern. And what we see, I'll give you 3 examples of signals that we might put on here. This is working very well for a 32 gigabaud carrier. That fits nicely into a 50 gigahertz grid spacing. A low baud rate signal, though, would be wasting lots of capacity because it's a very narrow signal and it's got lots of space in the grid slot around it. So that's stranded capacity. You can't use that. But then if you have ultra high baud rate signals, as we're now getting with modern transponders that can be up to 100 gigabaud, these are not compatible with fixed grid, this 50 gigahertz grid, because the grid spacing is too narrow. So what do? We moved to flexible grid. With flexible grid, we throw the idea away of fixed grid slots. We create flexible grid slots with 12.5 gigahertz granularity, and each flexible slot can be right-sized for the signal that it needs to carry. So in essence, you don't have grid spacings, and all of these signals could live happily in different parts of the fiber spectrum. And flexible grid systems, first of all, they waste less stranded spectrum, and secondly, they support high baud rate signals, and they are being used today for higher optical performance levels. So what have we learned about optical fiber capacity? Optical fiber acts as a waveguide. It traps the signal inside so that it can go further without losing integrity. A given pair of optical fibers has a practical capacity that's defined by things like the low attenuation bandwidth of the silica, the signal-to-noise ratio performance of the system, the amplifiers, and so on. And the lowest attenuation parts of today's fiber are in the C and the L bands. We have to be able to amplify the signals, and so EDFAs, Raman, and hybrid EDFA-Raman are the way that we use amplifiers today. The wavelength multiplexing grid also affects capacity. We can move away from fixed grid systems towards flex grid systems. You may still have fixed grid systems in the metro. Metro networks are probably less likely to be stressed in terms of capacity. So maybe you're not under stress to move to a flexible grid. So now I'd like to take a look at the evolution of transponder technology. So before we had coherent transponders, which I'll talk about in a moment, we had direct detect. And direct detect transponders are very, very simple. It's almost like Morse code. If there's light, it's a 1. If there's no light, it's a 0. Slightly more tricky than that, but that's really simple technology. But that suited us fine for transmission at 2.5 gigabits per second per wavelength, or even 10 gigabits per second per wavelength. No problem. Simple transponders, simple receivers, and so on. The challenge was to scale that technology beyond 10 gigabits per second per wavelength because of various impairments in the optical fiber. So these are linear impairments, and one of the downsides of a direct detect system like this, a direct detector is not a linear detector. It's actually a square law detector. And if you try to compensate mathematically for linear impairments with a square law detector, that gets very complicated. So we can add to our fixed grid table with the maximum wavelength data rates we could achieve with direct detect. So 200 gigabits per second in a 20-channel system, scaling up to 1.6 terabits per second in the C band of a 25 gigahertz grid system with 160 channels. So this capacity evolution took place from about 1995, which is when WDM became commercially available, up to about 2007. That was driven by higher quality wavelength multiplexing components. The 10 gig transponders had been available since about 1998, and 10 gigabits remained the wavelength data rate until about 2007. But then what happened is that we suddenly get access to commercial coherent transmission. So what is coherent? It just means anything to do with phase. But in terms of the commercial definition that we use today, we have phase modulation in the transmitter. Phase modulation is more tolerant to optical impairments, and you can put more bits into each modulation symbol. So if you're modulating at the same baud rate, you're now carrying more bits per second. You have a coherent detector as well in the receiver. It's now a linear detector. So that's really good because we can now apply powerful digital signal processing to compensate for linear impairments. And it also includes a laser in the receiver. It's called the local oscillator laser, and that acts as a very low noise amplifier in the receiver. And finally, we have this magical digital signal processing. Initially, it was only in the receiver, but in the last few generations of coherent, it's been in the transmitter and the receiver. And we can compensate for linear impairments. We can compensate to some extent for non-linear impairments. That's a bit harder. It's very computationally intensive, but we can do a little bit of non-linear processing and lots of other processing options. In fact, I'd like to give you an example you could do at home of how to encode a digital signal using phase. So here is the digital signal that we want to encode, 1001. Now, what could we do? Well, if we assume that in phase is a 1 and out of phase is a 0, what household item has phase as a property? Toilet rolls, right? So if you notice, a toilet roll has two layers, right? Two plies. And sometimes you look and at the perforation, the two plies line up. And sometimes they don't. And here is an important tip. If you want to convert between out of phase to in phase, you just take the outer ply, you pull it round and then rip off at the nearest perforation. Now you've changed between in phase to out of phase. So you could arrange 4 toilet rolls and have a 4-bit signal that you're carrying. Now that's not exactly practical for a high-speed internet connection. So what we tend to use are modulation constellations. So here's an example of some modulation constellations. This is a really simple one. Instead of 2 phase states, we now have 4 phase states. You'll notice the 4 dots. Each one of those dots represents 2 bits. And if we send one of those modulations on the X polarization and send a different one on the Y polarization, we now have 4 bits in each modulation symbol. And we call this polarization multiplexed QPSK, quadrature phase shift keying. And the great thing is we can now put more and more symbols into the constellation. So we have 8 QAM, 16 QAM, 32 QAM, 64 QAM. And the difference between Polmux QPSK, which carries 4 bits per symbol with the X and Y polarizations, up to Polmux 64 QAM, that carries 12 bits per symbol on the 2 polarizations. So as we increase up to that high order modulation, we actually multiply the spectral efficiency and potentially the capacity of the fiber pair by a factor of 3. So you'll say, my goodness, I want to use 64 QAM everywhere. You might not, because you also have a 30 times reduction in optical reach when you move to this higher order modulation. And you can kind of see why. If you look at the 64 QAM constellation, any adjacent symbols look very, very similar. Whereas if you look at QPSK, the adjacent symbols are on literally opposite sides of the constellation. So it's a lot harder to differentiate adjacent symbols with 64 QAM than it is with QPSK. That's one of the reasons why you end up with a shorter reach. But the 5 generations of coherent transponders that we've seen in the industry so far have actually exploited this ability to operate with more sophisticated constellations and run at higher baud rates. So this is roughly the date of commercial availability. And then you see that we've moved from the first generation, which could only run at 32 gigabaud with QPSK, right through to today's 5th generation, which even uses a very special kind of modulation called probabilistic constellation shaping, and at 100 gigabaud data rates. So on the bottom line, you can see the enabling technology that allowed us to do that, which is that the feature size of the ASIC technology drops from about 65 nanometers right down to today's 7 nanometer technology. Now, your iPhones are already using 5 nanometer technology, but there's always a bit of a delay getting from consumer devices into embedded devices like transponders. But 5 nanometer and then 3 nanometer would be the next steps. These are the performance boosts that we get, rising from about 40 gig per wavelength with the first generation up to 800 gigabits per second per wavelength on today's technology, and C-band capacity rising from 8 terabits right up to 42 terabits now in the extended C-band. And there are lots of other features in transponders that I don't really have time to talk about. These would require an entire separate tutorial. They're all about improving optical performance. right? That's how you get to this 42 terabits in the C band, 80 terabits or so in the C plus L bands. And the transponder performance evolution has really carried us through from direct detect right through to the coherent detection generations. And the wavelength data rate increase I calculated is a 320 times increase, and the C-band capacity increase is somewhere over 200 times increase. So we've done well over the last few years. So a summary of the transponder evolution: coherent transponders have certainly revolutionized long-haul transmission. We're in the 5th generation of that today with the 800 gig generation. Historically, transponder upgrades were the easiest way to increase fiber capacity on existing routes. Remember my 3 levels of options, right? This is option 1. You're following the transponder evolution curve. You don't have to change your optical fiber. You don't have to change your line systems. Coherent performance is predominantly driven by ASIC technology and also by the quality of the modulators. We're currently on 7 nanometer ASICs. The next stages are 5 nanometer, then 3 nanometer, and we're starting to max out in terms of capacity limits in the fiber. But what we can still do with transponder evolution is give you higher wavelength data rates at a given optical reach, because that will positively affect your network economics. So independently, we can expect optical performance in pluggable form factors to improve dramatically, because right now, the high performance transponders are not in a pluggable form factor. They're in a larger form factor where we don't need to worry about power consumption, we don't need to worry about heat dissipation, it's all about optical performance. But if you want to fit in a pluggable form factor, you have to stay within the power consumption of the MSA, you know, the spec for the pluggable, and also the heat dissipation for that. So pluggable performance is going to improve over the next few years. What about the interaction between the fiber and the transponders? So one of the interesting things is that optical fiber has evolved over the years, and it was always in search of the perfect fiber for the transponders that were available at that time. Many of us will be familiar with good old G652 fiber, which was, so the dates I'm using here are the dates of the ITU specifications for those fiber types. So G652 was specified in 1984. This is the perfect fiber for single wavelength operation at 1310 nanometers. Because guess what? The single mode or the fiber lasers that we could, the lasers that we could build back in 1984 operated at 1310 nanometers. We couldn't build longer wavelength lasers at that point. Well, we could in a lab, but not commercially for telecoms purposes. But then what happens, somebody says, oh, we can now build lasers at 1550 nanometers. And it turns out that G652 has very high chromatic dispersion at 1550 nanometers. So somebody invents G653 fiber, and that's the perfect fiber for single 2.5 gig wavelengths at 1550 nanometers. It has 0 dispersion at 1550 nanometers. So then we have another version of fiber that comes out, G655, which is the perfect fiber for single 10 gig wavelengths at 1550 nanometers. So all of these are essentially predating DWDM. Once DWDM comes along, that G655 fiber and the G653 fibers, they look very bad in terms of their nonlinear performance, because once we start putting EDFAs into the fiber chain, we're boosting the optical power levels so much we could easily trigger nonlinear effects. So G655 Leaf is invented as the perfect fiber for DWDM 10 gig at 1550 nanometers. So this is for 10 gig transmission now, it's not for coherent transmission. So the question arises, which is the best of these fibers for modern coherent transmission? And in fact, we have a winner with good old G652, because if you look at all the properties that these different fibers have, effective area and chromatic dispersion, in order to minimize nonlinear penalties, we need a high effective area and we need a high chromatic dispersion. Well, now that we're using coherent transponders, we can compensate for high chromatic dispersion, so we don't mind the high chromatic dispersion in a G652 fiber. It's quite ironic that the oldest kind of fiber, single mode fiber around, is actually one of the best fibers for coherent transmission. Although, of course, it would now be more modern G652 fiber. Apparently about 90% of the fiber in the world is G652, so that's probably very good news. We have new commercially available fiber types with ultra low loss G652. There's a large effective area family of fibers, G654 fibers. They're used in some submarine cables. There are terrestrial network variants of these. The larger effective area means you have a lower nonlinear penalty. Raman amplifiers don't work quite so well on those large area fibers, but they're not bad. So that's an option as well. And there's a lot of work on reducing the outer diameter, cladding diameter on fibers, so that you can fit more fibers into a bundle, a cable bundle. A 20% reduction in cladding diameter gives you a 50% increase in fiber pairs. So how far can we push capacity on existing fiber using existing line systems and only changing the transponders? Well, really, we're kind of almost there. Line systems that are commercially available today, you're looking at about 40 terabits in the C band and 40 terabits in the L band. Moving to Super C and Super L will increase that by about 25% in each of the bands. So you've got 50 terabits in your C band, Super C band, 50 terabits in your Super L band. And beyond that, we're getting closer and closer to the practical limits. But there is some gas left in the tank in terms of increasing the wavelength data rates. Capacity at longer reaches is interesting because those capacity numbers that I've just been talking about will give you an optical reach of about 1,000 kilometers. If you need to go further, let's say 3,000 kilometers, you'll reduce the capacity of your fiber down to about 75 terabits per second across those two bands. And then if you go ultra long haul distances, you'll drop to about 50 terabits per second. So can we transmit in other wave bands in order to increase fiber capacity? And the answer is yes, but it's not really for increased capacity that we're using it today. I've been describing dense wavelength division multiplexing, DWDM, and in DWDM, we have to wavelength lock our lasers. We use active cooling on the lasers to make sure the lasers stay on that same wavelength. That is more expensive than something like coarse WDM, where you don't have these cooled lasers, they're just free running lasers, and they wobble about a bit. So because you know that they wobble about a bit, you make sure there's lots of space between adjacent channels in coarse WDM. But you're using all of the other wave bands, the O band, E band, S band of the optical fiber. But the reach is a lot shorter because remember the attenuation in those other bands is much higher. So we use CWDM because it's cheap, not because of additional capacity. And it's typically a 10 gig per channel, only a few channels, and it's used in unamplified short distance applications. But it is proof that we could use these other bands. In other words, we can build lasers that can transmit across any of these bands. These optical fiber wave bands essentially evolved as laser technology did. The very first lasers we could build operated at the very edge of the visible spectrum, 860 nanometers. Then we had 1310 nanometers, and then we had 1550 nanometer lasers. So we can build lasers across any of these wavelengths, and today, of course, we operate in the C and L bands. And we solve for attenuation, even at this very low level attenuation, we solve for attenuation using amplification. And we can amplify in these other wave bands as well. And so here's our attenuation curve for optical fiber. And by changing the kind of doping element that we're using, we can amplify in different bands. So in the C and the L bands, we're using erbium. In the S band, we use thulium, which is a different rare earth element. In the E band, we use neodymium. And in the O band, we use praseodymium. Now, none of these amplifiers are commercially available. What happens is that academic researchers have demonstrated that they can amplify across these other bands. So these will all cost more per gigabit per second per kilometer than a C or an L band system. And I see that as the real problem of multi-band communication. Because the other funny thing about these other bands, the black line, or I think it's black line that I drew there, that is the dispersion profile of fiber. Chromatic dispersion is much lower, and also the effective area of the fiber, the same fiber, has a lower effective area, because effective area has a wavelength dependency at these lower, shorter wavelengths, which means that your nonlinear penalties are much higher at these shorter wavelengths, which is a bad thing. So if you think about wideband communication, applying that to the networks that you already have installed, you've already established the spacing between your amplifier sites. You can't really move them closer together. So optical performance is set by the performance in the C and the L bands. And the other wave bands, they have higher attenuation, and it would mean, you move your amp sites closer together, or you accept lower data rates per wavelength in order to close that link with the same amplifier spacing. Well, that's going to cost you more per gigabit per second. So I think there's potentially a much simpler solution in a lot of terrestrial networks, and that is more fiber pairs. So if you think most operators today use 1¼ inch ducts for their fiber, and historically the limit of the number of fiber pairs in ducts like that would be 864 fiber pairs. But today you can buy 1,728 fiber pairs for a 1.25 inch duct. So that's a really straightforward solution to increase capacity. And of course, it's just regular fiber that you'd use in the C and the L bands. So it's very straightforward to increase capacity. If you have 2-inch ducts, like a lot of the data center operators are installing, you can buy 6,912 pair cables these days, which is an astonishing amount of capacity. So what have we learned about fiber so far? Minimum fiber attenuation is in the C and the L bands. We could use other bands, but they're going to cost us more. Wideband transmission has been proven by coarse WDM, but CWDM is not used for higher capacity. It's because it's cheap. Fiber design has also evolved to match optical transponder capabilities as wavelengths, as lasers were available at longer wavelengths, as we move to DWDM, and as we use optical amplifiers. But good old G652 fiber is still the best, or is a very good fiber for modern coherent transmission. And more fiber pairs are a quick and easy way to increase capacity. Now, we really need to start looking at other fiber types. And I have a special mention here of a fiber type called ZB-LAN. And it's called ZB-LAN because it's an exotic mix of these fluorides: zirconium, bismuth, lanthanum. It's written down here aluminum, but I would call it aluminium, and sodium, which is a chemical symbol is Na. So that's where you get the ZB-LAN name from. It's generally today not used for transmission fiber. ZB-LAN is designed for things like gratings and gain fibers and so on, but people have actually made experimental lengths of ZB-LAN fiber and found that it has a very wide bandwidth compared to silica-based fiber and good nonlinear performance as well. Sounds fantastic. The bad news is it has to be made in zero gravity. This is one of the experiments that was taken up to the International Space Station, and unless we can find a way to sort of get, it's all about the crystalline structure within the ZB-LAN fiber itself. Unless we can find a way to make it on Earth, I don't think this is really a viable option. Can we really make tens of millions of kilometers of that? Well, maybe. So let's move on to another approach, which is few mode fiber. So remember I said that normal optical fiber is single mode. But if we make the core of the fiber a little bit wider, Instead of there just being room for one mode, we may have room for multiple modes. And these modes actually do take different path lengths along the fiber. And one of the problems is that you'll end up with lots of crosstalk between these modes because of modal dispersion, and you have to figure out what to do, how to unscramble these signals. But we can do it. The technologies, some of you in the 5G area may be aware of MIMO technology for multiple aerials. It's an established technology, so we could do it, but it would mean the development of specialist MIMOs for transponders. And the initial experimental results are looking like 2 to 3 times the capacity compared with a single mode system. And you could probably use a lot of the existing technologies for amplification and so on. But it does require new fiber. Single mode fiber doesn't work this way. You have to use few mode fiber. What about multi-core fiber? So this is a really interesting option. When you consider the size of these structures, it really is a form of nano-engineering, I think. It's a fiber that's designed to have multiple cores within the same cladding. And this is a form of space division multiplexing because we're transmitting across multiple fiber cores here. And the capacity of the fiber is now multiplied by the number of cores, which sounds like a good return. So there are, generally speaking, 2 types of multi-core fiber, uncoupled and coupled core. I'm going to look at the transmitter and receiver impact first. For uncoupled, what we mean here is that there is no interaction between signals in the different cores. They just travel in parallel. And that means that you don't need any kind of MIMO for compensation. You don't need to unscramble the signals at the other end. With coupled multi-core fiber, you do get a crosstalk between the cores. It's designed that way. And it means that at the receiver, essentially, you've got a scrambled mix of the signals on the 2 cores, and you need to have one of these MIMOs and a digital signal processor to separate the 2 or more signal streams. So that's at the transmitter and receiver, and you can probably agree with me that uncoupled clearly has an advantage here because we don't need to develop new transponder technology. Well, what about at amplifier sites? Well, at the amplifier sites with uncoupled multi-core, you actually have to fan out the different cores, amplify them in their own EDFAs, and then fan them back in to the next hop fiber. So with coupled multi-core, people haven't really got this to work yet, but the thought is you could have a single EDFA that will amplify all of the different cores. So I think at the amplifier sites, we could agree that coupled multi-core fiber has an advantage. So, there are pros and cons for each of them. So if we think about the likely scenarios here, the challenges here, when you talk to fiber manufacturers, they talk about potentially having very low yields. Because if you make multiple cores in the fiber, you can find you have one of the cores being bad, but you just have to throw the whole fiber away. You can't, like Intel used to make multi-core processors and they had bad cores and you could just turn that core off and sell the processor anyway. You can't really do that with multi-core fiber. In terrestrial networks, I don't think there's a practical use case here for multi-core fiber, unless space in the duct eventually becomes a problem. Because large fiber count cables seem to be a much more straightforward approach to solving the problem. Now in submarine networks, this is a different story. I've got a section at the end specifically on subsea. There may be a use case for 2-core and 4-core fibers. The reason I limit it to 4 cores, once you go above 4 cores, all multi-core fiber becomes coupled. But at 4-core and 2-core, you can design uncoupled cores. And the likely time frame for that has to be beyond, say, 3 to 5 years, because if you talk to the manufacturers of submarine cables, none of their roadmaps involve multi-core fiber today. So the good news is with uncoupled multi-core fiber, there's no need to change any existing transponders. They'll work on the multi-core fiber, but coupled core multi-core fiber is going to need new transponder designs. Right, moving away again from conventional fiber, this time to hollow core fiber. Because what have I told you so far about glass core fiber? Well, the fiber acts as a waveguide, it's single mode operation, and the attenuation varies with wavelength. Today's optical communication is in the C and the L bands. That's one of the things that limits fiber capacity. But there's so much more potential capacity in the fiber because we can build lasers over a much wider range of wavelengths. Glass is a nonlinear medium, which is also a limiting factor because that limits the optical power you can put into the fiber. If we could transmit at higher power levels, we could go further and at higher data rates. Glass core fiber has a higher latency than transmission through air because glass has a refractive index of about 1.5. Air is very close to 1. It's almost the same as a vacuum. Now that's an entirely separate issue from capacity. It's about low latency communication. Which means that a wider bandwidth waveguide would allow us to increase capacity reach. A waveguide that had more linear performance would allow us to increase capacity reach. And as a separate market driver, it would be great to find a waveguide that has lower latency than glass. All of these are limitations that come from using glass as the transmission medium. So what happens if you don't? What happens if you build a hollow core optical fiber? Now the potential advantages, because we're really transmitting in air, although the latest, I think, fibers are actually using a vacuum in the fiber. Wideband transmission, because we're not transmitting in glass anymore. Lower nonlinear effects, maybe much lower nonlinear effects. People have talked about several orders of magnitude lower nonlinear effects, and lower latency. So how's it work? Well, the first thing we've got to figure out is how to create that waveguide principle, how to trap the light within the optical fiber. So the very first hollow core fiber used a technique called Photonic Bandgap. So that was back in around about 1991. Now, I'm not going to explain these techniques, it's quite complicated, but Photonic Bandgap seems to be falling out of favor at the moment. It's at a bit of a technology dead end because we can't get the attenuation of Photonic Bandgap fiber low enough. So instead, an approach that first was proposed in 2011 is using an anti-resonant effect as the containment. And the most advanced fiber today is known as dual-nested anti-resonant nodeless fiber, or NANF, or DNANF, which is, this is the record holder at the moment. And it's mostly a great British invention. I say mostly because although the very first paper was proposed at the University of Bath in 1991, that's on Photonic Bandgap fiber, the first anti-resonant fiber was actually proposed by Andrei Primakov at the it was the Russian Academy of Sciences. So he actually came up with the idea of anti-resonance, but all the latest developments in anti-resonance have been at Southampton University in the UK. And they've now been commercialized. Another evolutionary view, the top line is showing the structural evolution from photonic bandgaps with lots and lots of little honeycombs through to anti-resonant structures, but then the bottom line is where they discovered this nested structure idea. And it's just scary actually how tiny these structures are. If we look at that bottom right one, you can see those circles. These are actually tubes of glass through the fiber itself. The outer diameter is classic 125 micron fiber. The larger tubes on the inner structure are I think they're, what are they, about 30 microns, and the smaller tubes are about 10 microns in diameter. And what they do, they tune the relative sizes of these to reduce attenuation at different wavelengths. So those structures are very precise as well as being tiny. So the big news that was announced at OFC earlier this year is that this company Luminicity, which is actually the commercial spin out from Southampton University, have announced this incredibly low attenuation DNANF fiber. 0.22 dB per kilometer at 1310 nanometers, and less than 0.18 dB per kilometer at 1550. Well, that compares with regular SMF. Now you'll see SMF has a much higher attenuation at 1310 nanometers, and it has a slightly higher attenuation at 1550. If you look at SMF 28 ultra low loss, it's still higher attenuation at 1310 nanometers. It's almost the same at 1550. So we're getting a fiber now that is performing not only as well as SMF 28 ultra low loss, but also over a much wider band of wavelengths. So this is really where we're getting the additional spectrum from with hollow core fiber. And this gives you an indication of latency changes, glass core versus air core fibers. So basically, you're dropping from just under 5 microseconds per kilometer of latency in glass core fiber to about 3 1/3 microseconds per kilometer. So it's a decent reduction in latency. Now, the pros and cons, the likely scenarios, well, clearly hollow core fiber offers a number of advantages over glass core fiber: lower latency over a wider band of wavelengths. The other thing to mention about the lower attenuation is that glass core fiber is approaching its theoretical minimum attenuation, whereas hollow core fiber is nowhere near its theoretical minimum attenuation. So potentially we could have a couple of orders of magnitude more reduction in attenuation in this fiber. So there are no modifications needed to the transponders. You can use regular transponders. And the big question, can you manufacture it? You saw the intricacy of those structures. Can you manufacture at high yields? How much will it cost? If you can manufacture this fiber, will it be really usable and durable in real deployments, including subsea? What happens if a hollow core fiber that has a vacuum inside the fiber has a cable break under the ocean? You've now got 3,000 or 4,000 kilometers of fiber full of seawater. So that's probably not an ideal situation. I don't know how you kind of recover from that. Will existing amplifiers work on hollow core fiber? All of the trials of hollow core fiber today have been unamplified. And how can we repair these fibers? If you're in the back of a truck on a rainy day next to a freeway and you're repairing hollow core fiber, how long is it going to take you? How many times have you got to fusion splice that fiber before you get a good splice? So a special topic here is submarine cable capacity, because the biggest difference between terrestrial and subsea is power supplies. In a terrestrial network, you have amplifier sites, but you also have mains electricity at those amplifier sites. You can put electricity in at all of those amp sites. You may not be able to put as much as you want, but you can put it in all of these sites. In a submarine cable, you can only put the power in at the ends of the cable. So if you have a 6,650 kilometer transatlantic cable, you can only put the power in at the landing stations at either end. And so at some point, the conductor of that cable can only take a certain electrical load. And that's what's limiting the number of fiber pairs that you can fit into a submarine cable these days. So capacity expansion, the approach in submarine cables is to focus now on the total cable capacity. Previously, until very recently, the focus was on fiber pair capacity. So what happens is that by tuning for wider amplifier spacing in the cable, lower amplifier power, you can also do sharing of your backup pump lasers, because remember, these amplifiers in a submarine cable, they live under the ocean for 25 years. So if your amplifier pump lasers burn out, you can't lift the cable and replace the amplifier housing. That's very bad. That's very expensive. What you do, you put backup lasers in those housings. And normally it's 1-for-1 backups, which uses a lot more power. But if you can find ways to share backup pumps between all the different fiber pairs, you could economize on power. And we refer to that, it's an architectural design approach for submarine cables as space division multiplexing. So if you ever listen to a submarine presentation, you'll now hear about SDM. And SDM has its own roadmap of developments. So before SDM, the maximum transatlantic cable capacity was about 250 terabits per second. And that assumes fifth generation transponders. That will be a cable like the Maria cable, which is actually the highest performing cable from a per fiber pair point of view, but the total cable capacity is not as much as more modern cables like the Dunant cable, which probably has about 300 terabits per second on 12 fiber pairs rather than 8 on Maria. There's a cable planned now, transatlantic, with 24 fiber pairs, which would have about half a petabit per second of capacity. And then we know how to build a transatlantic cable which could give a 1 petabit capacity. So that's not in planning at the moment, but all the technologies are lining up that cable could be built. So is there a fiber pair limit in submarine cables? Yes, because there's a limit. So if you imagine submarine cables they are engineering miracles. They live in incredible conditions, salt water at massive pressure for 25 years. The cable designs themselves have been certified in similar ways to like satellite technology or space technologies. They are very, very highly certified. There's only a certain number of fiber pairs you can fit into those tried and tested cable designs. Once you go beyond that, you need to start developing those designs, and that's non-trivial. That's going to take a lot of testing. And also, the more fiber pairs you have in the cable, the less cable a ship can carry in its hold, and that's going to negatively affect your deployment economics. There is another aspect as well. If you have a lot more fiber pairs in a cable and you have a cable break, it takes you longer to fix the cable. So a lot of these are sort of pointing towards, well, maybe instead of putting more fiber pairs, maybe we use multi-core fiber. So that's probably the driver behind the change to multi-core. So future fiber types in submarine cables, if you look at wet plant vendor roadmaps, there are no new fiber types for the next 2 years. So the current fiber types will deliver up to this 1 petabit transatlantic performance. But beyond that, I think we probably have to start looking at multi-core uncoupled fibers. That would be a good next step. And that solves for that cable diameter problem. Hollow core fiber, it's a very interesting technology in submarine deployments because of the potential for higher capacity and much lower latency. And it potentially solves 2 problems at once. But of course, hollow core fiber at those pressures, and what about if you have a vacuum in that fiber and it breaks, and there's a lot of question marks really to be answered there. Now, one of Meta's network architects, submarine network architect, Dr. Steve Grubb, he actually has coined this term of Neptune's law for transatlantic cables. Similar to Moore's law, this exponential rise. So the 2 lines that are shown there are for cable capacity and the cost per gigabit per second. So Neptune's law says that submarine cable capacity roughly doubles every 2 years, and that the cost per gigabit per second will halve every 3 years. And you can see that there's a discontinuity there. And the way that Steve explains that discontinuity, he says, well, you think about the timing of the dot-com collapse, there wouldn't have been a lot of investment at that after that period in submarine cables. So the slope to the left of the discontinuity for cable capacity is steeper. And also, the slope actually includes the advent of the EDFA. And that was a real bonus. That's like a one-time boost that you get in cable capacity because you're now dealing with multiple wavelengths. And as transponders evolve, those wavelengths are carrying more gigabits per second. So what he also shows are the enabling technologies along that curve. We have forward error correction technology that boosts capacity. We have the EDFA, then the emergence of WDM, then Coherent comes along, and then we have large area fibers and high positive dispersion fibers, and the latest technology is SDM. But there's also a slightly whimsical progression here of conventional wisdom. It's like at the beginning, the far left, it shows coherent is the future. But that wasn't the coherent that we know today. It was using coherent as a low noise amplification technology. And as soon as EDFAs came along, that kind of coherent research started to drop away. So then, we have these different technologies. Coherent becomes the future beyond the discontinuity. Dispersion is now our friend. So we have these changing views of how you design submarine cables. So a summary of submarine cable capacity evolution. Historically, we have transatlantic cable capacity that's doubled every 2 years. The cost has halved every 3 years. And until recently, the focus of development was on fiber pair capacity. It's now changed that on the highest quality cables, we're now reaching the limit of what we can achieve per fiber pair. And so the focus changes to cable capacity, total cable capacity, and that's where SDM comes along. So SDM has this roadmap of architectural design that takes us to a 1 petabit per second transatlantic cable using proven technologies. It's only after that we need to start thinking about more advanced technologies like multi-core fibers and so on. And there are practical limits on the number of fiber pairs that you can put into a transatlantic cable. So multi-core fiber is very interesting, solves the problem of the size of the cables. And hollow core fiber, again, is very interesting, but there's a lot of challenges, I think, associated with hollow core. So it could well be, if you looked at terrestrial future cable types, you may see the emergence of hollow core fiber initially for low latency applications. But then if you look at subsea cables, you're more likely to see multi-core fibers, I think, appearing in those kinds of cables. So let me try to summarize all of these options. I know I covered a lot of ground here. And I do apologize because this slide does not follow NANOG guidelines of having at least 24-point text. I couldn't use 24-point text. It's really for you to look at afterwards and use as a kind of guide. So of course, I'm looking initially at commercially available solutions, and then at future technologies. And the commercially available solutions, remember I divided them down into those 3 categories, where you're using the same fiber or today's fiber with today's line systems, moving to existing fiber with new line systems, and then finally new fiber deployments. And then in future, and of course the investment rises as you move from left to right there. Now, in the future technologies, there's multi-band, there's multi-core fiber, multi-mode fiber, and hollow core fiber. So there, the question you asked there is, what is the risk of choosing a technology that isn't going to catch on from a commercial point of view? The likelihood of commercial deployment. So on the left-hand side there, the commercially available solutions, transponder upgrades. I didn't cover it here because it's quite a complex topic, and it's very dependent on the individual fiber pair operator, but it's about reducing the margins on your network. Some operators still have lots of safety margin in their networks, and by reducing that, you could potentially get a lot more capacity. Then you have the options for squeezing out more capacity on existing fibers by upgrading your line systems, moving to flexible grid, Raman amplification, C+L, and then Super C, Super L. And then the new fiber deployments, of course, we've got ultra low loss SMF28, we've got large area fibers, and we've got these reduced cladding fibers that mean you could have high fiber count cables. So then multiband, of course, I think there are lots of questions with multiband. It's a mixed picture. I'm not sure it's going to pan out economically with multiband. Multi-mode fiber, I covered it very briefly, the few mode fiber experiments. That does mean you have to develop new transponder technology. Multi-core fiber, we have the uncoupled and coupled core. I think uncoupled definitely has a future because, again, you don't need to develop new transponder technology. And then hollow core fiber, we have these two different approaches of photonic bandgap and anti-resonant. Photonic bandgap seems to be a little bit of a dead end at the moment. That might change, who knows? Somebody has a breakthrough and that situation changes. But right now it's nested structures, it's anti-resonant structures. And the focus has tended to be on low latency applications, financial trading. BT has a really interesting deployment for 5G front haul. So they can increase the distance from the radio mast to the CUDU by 50%. And that changes the economics of how you deploy 5G networks. And that's because of the lower latency of hollow core fiber. We haven't really explored capacity expansion with hollow core fiber. And I've got a little animation there that says yet. At some point we will, but that involves figuring out how to amplify on hollow core fibers. So I think that's probably my last slide. Happy to answer questions if I can, but thank you for your attention.
Hi there, Joshua Telstra. So subsea obviously is the area of greatest interest to me because you've got all these assets in the ocean. You really don't want to change them. So I'll admit I'm really focused on the far left of your slide in transponders. When you look at high QAM technology, the issue with reach is distinguishing the different symbols once you're at high QAM. I was wondering, we've seen a lot of work with AI systems over the last few years where they can use neural nets, trained models to reduce noise out of image processing far in advance of what we used to be able to do with standard methods. Has anybody taken such computational technologies and applied them to resolving high noise signals on optical fiber?
So using machine learning, particularly, there are two ways to use this in subsea networks. One is by analyzing the performance over the life of the cable, so that you can predict if you're getting close to your margin limits. As you tend to design cables with a certain end of life margin, and if you could reduce that because you're going to change transponders in 3 years or 4 years, then that might be interesting to understand how those margins change by feeding a kind of big data model and throwing machine learning at it. That's a non-real-time approach, obviously. I think what you're describing is a real-time approach, and where that's being used, or the way I know at the moment that it's being used, is in nonlinear compensation techniques. So there are methods of machine learning for nonlinear compensation. So, and that would be a noise reduction. That's a form of noise reduction. But in terms of like ASE noise reduction and those aspects, I'm not aware of that at the moment. And it would have to presumably happen in the amplifiers, because that's the main source of noise that you get on the cable, which wouldn't work with existing cables. Yeah.
Hello, my name is Corbin, and I have a bit of a whimsical question for the last day of the conference. This is the first I've learned of hollow core fiber, but do we now have to acknowledge the vision of American Senator Ted Stevens when he said that the internet is just a series of tubes?
Well, I guess we better ask Al Gore. Didn't he invent the internet?
Yes. Patrick Gilmore, Meta. On one of your slides, you said these 3 things would require their own tutorials. Would you please come back and give all 3 of those?
Oh, I'd be glad to. Yeah, absolutely. Thank you. Yeah.
I'm going to give one more plug. If anybody enjoyed The Martian by Andy Weir, he did a follow-up book called Artemis, where ZB-LAN style fiber is a core plot point.
Oh,
so
cool.
If you enjoy that type of thing, pick it up. It's good reading for the plane.
Artemis, yeah, I will do. Yeah, thank you.
Artemis.
Thank you very much.
Thank you, James.
Thank you, Jeff. We appreciate that talk. I think speaking for myself alone, but probably several other people, we all are going away knowing far more about optical systems than we did coming into the room. So appreciate it.